All right, so let's go with some questions from our last quiz. Okay, let's go to the beginning. I'm going to go with some of the most missed questions. That's what I'm going to do. So let's start with, say, this question over here, where we have 28% correct response rate. Okay, so let me see. You are given this question. I'm going to take a screenshot first. At pressure 10 kilopascals, so here's 10, and then temperature 325, which is over here. So we are going to be meeting over here, right? We are at this point. Increasing the pressure at constant temperature will, so what we're going to do is we are starting at this point, and then we're going to increase the pressure. That means we are going to go up. Okay, I don't know to what point because the question doesn't specify, but we are going to go up when you increase the pressure like that. Okay, now the question is, it increase now what happens when you do this? Increase the kinetic energy of the system? No. Okay, the temperature remains the same at 325. Therefore, if the temperature is a measure of the average kinetic energy, if the temperature is constant, the kinetic energy is constant. Decrease the kinetic energy? No, we're not going to touch the kinetic energy. Okay, increase the average potential energy of the system. So when you go up, okay, we can think about this in different ways. Actually, when you increase the pressure, you force the particles to come close to each other. When the particles are closer to each other, you're going to get stronger interactions. The stronger the interactions, the lower the potential energy. Okay, let me write that down. The stronger the interactions, attractive interactions, okay, the lower the potential energy. Okay, so we are in other words, when we increase the pressure, you're going to be a decrease in the potential energy. Okay, so I mean the other way we can think about this, we know that we have wave pressure curves. Okay, wave pressure curves are gas liquid boundary. Okay, this is liquid, this is gas. Now the wave pressure curve is just one part of this phasor diagram, this part, right? So if you are above the line, you are above the curve, you are a liquid. If you are below the curve, you are a gas. And we say that when we increase the pressure, you go from gas to liquid. In liquid, you know that we have strong interactions because particles are closer to each other. Therefore, you're going to have stronger intermolecular forces, so stronger attractive interactions, meaning you're going to have a lower potential energy. Okay, so anyway, so increasing the pressure at constant temperature, okay, this will definitely decrease the potential energy. Now, the correct answer is option D. Okay, now that takes care of that. Let's move on to a different question. Okay, let's see, that is this one. Okay, I want to see question 5 as well really quickly. Let's see what's going on there. Okay, I mean it's the same thing, I believe. Okay, here's the wave pressure curve. Pressure 40 kilopascals. Okay, give me a second, I need to take a picture. Okay. So we are here when it comes to pressure, and then temperature 380 Kelvin, and therefore we are at this point. Okay, increasing the pressure at constant temperature is the same thing as before. People had trouble with that. Okay, if you increase the pressure at constant temperature, it doesn't affect the kinetic energy, it will only affect the potential energy. And then increasing the pressure will always decrease the potential energy because you're going to make the attractive interaction stronger. Okay, anyway, that should decrease the average potential energy. It should be this answer. Okay, moving on to the next question. We are around 60s. We will come back to it if we have to. Let's see, 80s, pretty good. Okay, close to 70s. The next question Question 7 seems to be good, but let's see. All right, question 8. Okay, we have some mixed responses here, but let's see what we have. Let's pick the lowest one. Question 8. Okay, in the first diagram, select the correct answer for the change of condition A to condition A to condition B at constant heating. Right. So here's what we have. Let me see. So when you go from condition A to condition B, let me actually take a picture first. Okay. So the difference between condition A and condition B is you can see that these guys are in the gas phase here in condition A, and they have gone to the liquid phase. Okay. So we're condensing when you go from condition A to condition B. So they're also saying that we are at constant pressure. Okay, and then what we're doing is we're changing the temperature to condense at constant pressure. We need to decrease the temperature. We need to slow down these particles so that we can facilitate the attractive interactions between them, and therefore the particles will condense, the substances will condense. That's the idea. Okay, so we need to be cooling. Okay, so far we know that we need to cool to get from condition A to condition B. Now let's see what the question is asking actually. All right, when you go from condition A to condition B, you have to decrease the you have to decrease the temperature. Decrease in temperature will decrease the kinetic energy. Okay, so the first two options are out because we are decreasing. It has to be decreasing the kinetic energy. Okay, and also when you do that, you facilitating strong interactions between these particles now. Okay, right, because they're closer to each other, and then if that happens, you're gonna have stronger interactions between the particles, mean you're gonna have a lower potential energy. So that's gonna decrease the potential energy as well. So the correct answer is option C. All right, so let's see. Yeah, there you go. Moving on. Let's pick another one from there. Okay. So it's the same thing. It's just the opposite here now, right? So we are going from, let's take a picture. Okay, we're going from condition A to condition B. What has happened is these particles have gone from the liquid phase to the gas phase, meaning at constant pressure, for this to happen, we need to heat, right? We need to heat up the system. Okay, and that's the only way we can do it. So it should be a heating situation. And then if we are heating, the kinetic energy has to increase. Okay, now for these options are okay, option B is out, and then option D is out, and then between options A and options C, we know that we have stronger interactions when the particles are in the liquid phase because they are closer to each other. And then in condition B, we have gone to the gas phase, meaning we have weaker interactions. That means potential energy has to increase. Okay, so there's an increase in the potential energy. Therefore, this is out as well. But the correct answer is option A. All right, anyways, let's move on. Let's try this Venn diagram question. Okay, now given condition A and condition B, select the correct Venn diagram for two conditions A and B. Okay, now again, the difference here is we have, let me take a picture first. Okay. Okay, so the difference between A and B is we have these particles in the liquid phase in condition A, and then they are in the gas phase in condition B. So if that is the case, we know in the gas phase we have weak interactions. That means we have a higher potential energy. Therefore, potential energy wise, A compared to A, B will have a higher potential energy. And also in the PEG diagram, we have a number of configurations. Always the gases will have a higher number of configurations than the liquid, because you have more gas particles in the in condition B. You're going to have a higher number of configurations in condition B. Therefore, it should be like this. And then if you drew the PEG diagram, the condition B has higher potential energy and a higher number of configurations, higher potential energy and a higher number of configurations than condition A. Therefore, correct PEG diagram should look like this. And then that looks like option D over here. So that should be our answer. All right. So yeah, moving on to, let's see, question 10 seems to be fine. Question 11 seems to be okay. Oh, we have a very low response rate for correct response rate for question 12. Let's pick one. Let's pick question 3. Okay, the ionic compound, you are asked to arrange them from lowest to highest potential energy. Okay, so lowest to highest potential energy means strongest to weakest ionic force. Okay, because we have ionic compounds here. Okay, now here's what we need to remember here. Okay, you can see the answer as well. That's fine. We can justify this now. The ionic force is directly proportional to the charge product, that is the charge of the cation times the charge of the anion, and inversely related to the distance between the ions squared. Okay, and then if you look at these species over here, okay, what I'm going to do is, first thing is to assign the charges. Okay, sodium is always +1, chlorine always -1, magnesium is always +2, chlorine is -1. Okay, and then calcium is +2, chlorine is -1. See, I'm only writing the charge of one anion here. Okay, even though we have two anions in calcium chloride. Okay, we just need the charge of one anion and one cation. All right, last one, calcium is +2, and sulfate, this is a multi-atomic anion, is going to be -2. Okay, just to remind you, we need to know the charges of multi-atomic ions. These are the ones we should at least keep in mind. Okay, sulfate 2-, phosphate 3-, nitrate 1-, carbonate 2-, hydroxide 1-, and NH4+. Okay, we want to at least remember these ones. Anyway, just to remember something. Okay, and talking about this, now the first thing that we need to look at when we determine the ionic force is the charge product. Okay, greater the charge product, stronger the ionic force. So let's look at them. The charge product wise, okay, here's the charge product. Let's look at the absolute value of that. Sodium chloride has a charge product of 1, magnesium chloride 2, calcium chloride 2, calcium sulfate 4. Therefore, you're going to have the strongest ionic force. Okay, ionic force wise, we're going to have the strongest ionic force in calcium sulfate. Okay, and the weakest in sodium chloride. That much we know. And then between magnesium chloride and calcium chloride, so here's the thing, magnesium and calcium are in the same group. Okay, the charge product doesn't cut it, but then we need to look at the size or the distance between the ions. So magnesium is a smaller ion. Here's magnesium. Let's say here's calcium. I'm sorry, here's chlorine. Here's magnesium chloride. Here's the distance between the ions in magnesium chloride. This is MgCl. Okay, and then when it comes to calcium chloride, calcium is a much larger ion than magnesium because it is down the group. Magnesium and calcium are the same group, but calcium is below magnesium. And then here's the chloride, which is the same size. And the distance between the ions in calcium chloride is about this much. Because you have a greater distance between the ions in calcium chloride, you're going to have a weak ionic force there, because when you have a greater distance between the ions, okay, then your interactions are going to be weaker. Okay, in class, we talked about how the long distance relationship will have weaker strength. Okay, weaker compared to when the people are closer to each other. Anyway, so that's the idea here. Therefore, the strength wise, ionic force wise, okay, sodium chloride will be the lowest, and then calcium chloride, and then magnesium chloride, and then we're going to have the greatest ionic force in calcium sulfate. All right, and then when it comes to the potential energy, all right, stronger the force, lower the potential energy. Therefore, the potential energy will be greatest in sodium chloride, and then calcium Cl2, and then magnesium Cl2, and then lowest potential energy will be calcium sulfate. Okay, so this should be our answer. Let's see if we can find that, and that's our option. Yeah, you can see that's our option 1. Okay, that's why this is the correct answer. Anyway, so moving on, I think the others are the same as well. Okay, let's look at one more just to be on the safe side. Yeah, it's the same issue here as well. Okay, so really quickly, the charge product wise, okay, +1, -1, +2, -1, +2, -1, +2, and minus. It's the same thing. Okay, instead of calcium sulfate, we have magnesium sulfate. Okay, so the lowest potential energy will be in magnesium sulfate. This is the lowest because you have the greatest charge product, meaning strongest ionic force, and then highest will be sodium chloride because we have the least charge product, meaning weakest ionic force. And then between magnesium chloride and calcium chloride, because calcium is a large ion, you have a greater distance between the ions here. Therefore, calcium chloride should have a higher potential energy than magnesium chloride. Okay, so that is that. Okay, anyway, moving on to the next question. Question 13 is fine. Let's take a look at one of these questions. Okay, question 14. All right, okay, I like this question. So basic aqueous solutions contain higher concentrations of hydroxide ions. Okay, now here's the thing. All right, we're talking about hydroxide ions. Then pure water. Which of the following substances could you use to prepare basic solutions? Okay, anyway, the idea is we need to get hydroxide ions in water. Okay, so the only way we can get, I mean, the way we can get hydroxide ions in water is we need to have a good way to get hydroxide ions in water is to have an ionic compound that is soluble in water that contains hydroxide ions. All right, so if you look at these options, CH3OH is not a good option because this is a covalent compound. Okay, covalent compounds do not dissociate into ions when you add in water. Okay, they just mix with water. So that is out. So all three is out as well because of the same reason. And CH3COOH, again, this is a covalent compound. This won't dissociate into hydroxide and something else. Okay, it's not possible because we don't have ions to begin with. Anyway, and then the last option is potassium hydroxide. This is great, okay, because we have the charge product here is +1 times -1, and then this is soluble in water because if the charge product is less than 4, they tend to be soluble in water. That's our prediction. Okay, so you can expect this to dissociate into potassium plus and OH minus in aqueous solution. Therefore, this is going to be the best answer. Okay, and this is true with, it could be sodium hydroxide, potassium hydroxide, let's say calcium hydroxide. Okay, so the magnesium hydroxide. Okay, so as long as they have hydroxide ions and the charge product is less than 4, you can expect them to produce OH minus ions in water. That's the idea. So this question is about solubility of ionic compounds that contains hydroxide ions, not about anything else. Okay. Anyway, that's why KOH is the answer for that question. All right, moving on to question 16. Let's see, let's pick this question over here. NH3 reacts with oxygen to produce NO, NH2O. Identify the limiting reactant represented by the following submicroscopic representation of the initial state of the reaction mixture. Okay, so okay, you are given the initial state of the reaction mixture and you are asked to identify the limiting reactant. Now let's see how to handle this. Now, first of all, we need to check whether this equation is balanced. All right, obviously not. We have one nitrogen on the reactant side, one on the product side. That is balanced. We have 3 hydrogens on the reactant side, but only 2 on the product side. That we have an issue. And then oxygens are balanced, okay, as of now. So I think what we could do is to have the same number of hydrogens on the product side. Let's see if we can try to do it. Okay, we can multiply the number of H2O by 3/2. Okay, that will give us 3 hydrogens on the product side. Now that's going to be that's going to give us a problem because we're going to have 3/2 oxygen plus 1. So 1 plus 3/2 is 2/2 plus 3/2, which is 5/2. We need 5/2 oxygen atoms. Okay, on the reactants, on the product side, we have 5/2 oxygen atoms. Okay, and then on the reactant side, we have only 2. Now, we need to multiply the number of oxygens on the reactant side by 5/4. Okay, we just divided what we have, O2 by 2, and then multiply by 5/2. So it's how we get 5/4. Anyway, and then if we multiply everything by, let's say 4 in this case. So we're gonna get 4 NH3 plus 5/2. Giving us 4 NO plus 3,6 H2O. Okay, let's see if this is balanced. 4 nitrogen, 4 nitrogens, 12 hydrogens, 12 hydrogens, 5 times 2, 10 oxygens, and 10 oxygens. So it seems to be balanced. Okay, so that's what we have. Let me see if I can okay, go to this submicroscopic representation. So what we have here is we have 1, 2, 3, 4, 5, 6 NH3, okay, reacting with oxygen. Okay, so give me a second. So what we have is we have 6 NH3 and we have 1, 2, 3, 4, 5, 6 oxygens in our initial state. Okay, now let's see what we need and what we have. Okay, so according to the balanced chemical reaction, according to this, okay, to react with 4 NH3 molecules, we need 5 oxygen molecules. Okay, so to react with, say, 1 NH3 molecule, we need 5/4 oxygen molecules. And to react with 6 NH3 molecules, we need 5/4 multiplied by 6 oxygen molecules, okay, which is gonna be, let's see, okay, 3 times 5, 15 divided by 2, 7.5. We need 7.5 to react with 6. Okay, this is what we need. And now, when it comes to what we have is 6 of this and 6 of this is what we have. Okay, so we need 7.5 of oxygen. We only have 6. Therefore, we know that oxygen is limiting our reaction. We don't have enough oxygen, meaning oxygen is limiting our reactant. Therefore, the limiting reactant must be O2. Okay, and that's how we determine the limiting reactant. Okay, so let's see. Yeah, here's the answer. Answer is O2. Okay, moving on. Let's take a look at question 9 over here. Formation of NO from nitrogen and oxygen is endothermic process. Okay, now this is a good one. I just want to make a point here actually. Okay, so here's the thing. In the question, you are told this is an endothermic process. You are given this data. If this is the case, we know that if it's endothermic, if you draw the reaction path diagram, okay, reaction path, reactants have a lower potential energy than the products. So products are over here, the reactants are over here. Okay, this is what endothermic means. Energy needs to be absorbed during the process. Okay, so if the products have a higher potential energy, this means that products, okay, have weaker bonds. Okay, so products have weaker bonds compared to reactants. So reactants have stronger bonds. Okay, I know that we talked about how we in class we talked about how we have AA bonds on the reactant side and AB on the product side. Okay, now if that is AB bonds tend to be stronger most of the time, 93% of the time. AB bonds are stronger than the AA bonds, therefore product should have a lower potential energy. Okay, we talked about that, but here's the thing, that is for prediction. Okay, so we use this AA versus AB argument for prediction only. Okay, so if you're not given any other data, if we were not told that this was an endothermic reaction, okay, then we have to go with AA and AB bonds. But because we are given the information about whether it's exo or endothermic, we need to go with that because the data is more powerful than our assumptions of models. Okay, so anyway, so that's the idea, and we know that we have weak bonds in products. Okay, so if you look at this, products have a higher potential energy. Good, because the bonds in the products are stronger. Nope, if it has a higher potential energy, okay, it should have weaker. Products are stronger. Bonds in the products are stronger is incorrect. Higher potential energy means weaker bonds. Products have higher potential energy, correct? Because the bonds in the products are weaker. This is absolutely correct. That's the correct answer. Third option, we don't have to read, but products have low potential energy is incorrect. We know it has a higher potential energy in the endothermic process. And option D, products have a lower potential energy. We're not going to read further. That is incorrect. Endothermic means products have a higher potential energy than the reactants. Okay, so the correct answer is option B. Okay, now moving on to let me see. Okay, I just want to check something. That's fine. Okay, anyway, let's move on to another question. All right, question 19 seems to be okay. Question 21. I have this question with 38% correct response rate. Let's take a look at it. Okay, a molecule has strongly polar bond XY, where X is much more electronegative. Okay, if X is more electronegative, all right, let's take a picture. If X is more electronegative, that means in the XY bond, X should have the partial negative charge because the bonding electrons will spend more time around X than Y. Therefore, X is going to have a higher negative charge, have a partial negative, high electron density, meaning partial negative charge compared to Y. Okay, so it should look like this. Okay. All right, then Y. which of the following statements are true? Okay, number one, the valence shells in Y have a lower potential energy than the valence shell in X. That is incorrect. Okay, so valence shells in X has a lower potential energy than the valence shell of Y. The reason is, okay, if X has a higher electronegativity, meaning the X nucleus has stronger attraction towards the bonding electrons. Okay, and then if X has strong attraction towards the bonding electrons, okay, that means X valence shell should have a lower potential energy than Y. Okay, because remember, the stronger the attractive interactions, okay, the stronger the attractive interactions, the lower the potential energy. That's the idea here. That is why one is wrong. Two, the outermost electrons in X have a higher ionization energy than in Y. That is absolutely correct. Okay, X is more electronegative, meaning X has stronger attraction towards the electrons than Y, and therefore it is harder for you to remove them because they're strongly attracted. Therefore, the ionization energy will be greater in X compared to Y. Okay, so that is correct. And Y will be partially negative? No, X will be partially negative because electrons are attracted more towards X. Therefore, you're going to have a higher electron density around X, meaning you're going to have a partial negative charge on X, not on Y. Okay, so only 2 is correct. So that's the correct answer. Okay, so moving on, you can see that that's the correct answer. Okay, and then let's take a look at question 22 really quickly. Okay, what is true about these molecules? We have 1 and 2. So here's the vapor pressure. If we have a lower vapor pressure, that means, so at any given temperature, let's pick one temperature, say X. No, I can't draw here. Let me see. Okay, at any given temperature, X, let's say that substance 2 has a lower vapor pressure than that 1. Okay, let's pick a temperature over here. Okay, you can see that the vapor pressure of 2 is much lower compared to vapor pressure of 1, meaning the substance 2 has a harder time to go from the liquid phase to the gas phase. Why? Because the particles are strongly held together in 2 compared to 1, because you have stronger intermolecular forces in 2 compared to 1. Okay, so because you have stronger intermolecular forces in 2, so we established that based on the vapor pressure. Okay, so we have stronger IMFs in 2. You know that if the IMFs are stronger, it's going to lead to higher boiling point, higher melting point, higher density, higher viscosity, and so forth. Okay, and also lower vapor pressure, lower volatility, and so forth. Okay, now again, we know that B has a higher boiling temperature than A, therefore B should correspond to 2 because it has stronger intermolecular forces. Okay, okay, higher boiling point means stronger intermolecular forces. Out of 1 and 2, 2 has strong intermolecular forces. Okay, now let's look at the answers. A corresponds to vapor pressure curve curve 1, right? Because it has weak interaction. That is correct. Okay, A has a higher boiling, A has a lower boiling point, mean weaker IMF. Okay, therefore vapor pressure must be high at any given temperature. Okay, so that is correct. B corresponds to vapor pressure curve 1. No, that is wrong. B corresponds to vapor pressure curve 2 because it has a higher boiling point, means strong intermolecular forces, and then in the vapor pressure curve, it is going to have a lower vapor pressure. B corresponds to vapor pressure curve 2 because it is more polar. No, that is not true. Okay, oxygen is more electronegative than sulfur. Therefore, I would expect A to be more polar. So this is incorrect. A corresponds to vapor pressure curve 2. That is incorrect. Okay, we already know that. That's That's not correct. So correct answer is option A. Okay, so moving on. Let's see. Yeah, there you go. Moving on to, let's see, we did random question 3 of question 24. Oh, look at this question 25. Let's pick the lowest one first. It's a huge range, actually. It ranged from 12.5% to 61%. All right, anyway, I need to address this. So let's pick question 6. Okay. Now, here's what we have. Okay, so let's take a picture. All right, the question is rank these in order of increasing strength of dispersion forces. Okay, dispersion forces is directly proportional to, let me erase that. Okay, the dispersion forces are directly proportional to the polarizability. Okay, and which is directly proportional to the total number of electrons, right? And then the size, okay? Higher the number of electrons, greater the polarizability, stronger the dispersion force. That's the idea, okay? Now, what we need to do is we need to determine the number of electrons, okay? So here we have bromine, okay? Bromine itself has 35 electrons. Atomic number of bromine is 35. That means when it is neutral, it has 35 electrons. So that's a lot. Okay. And then we have carbons. Okay. And then in the line structure, we know the enzyme bends are carbon, and the common bonding pattern of carbon is fulfilled by carbon hydrogen bonds. Therefore, we can have this situation. Okay. So we're going to have a lot of electrons here. Okay. So if you count the electrons, we have this is C3, H 7 and Br, so it's going to be 3 times 12 plus 7 plus 35, so 36 71 78 electrons here, right? So that must be really high when it comes to dispersion force strength. Anyway, if you look at something like option B, okay, same thing, C, this is what we have. Okay, and then if you count them, we have 3 carbons, and then hydrogens, 8 hydrogens, and 1 oxygen. That is 3 times 12 plus 8 plus 8, because oxygen is has 8 electrons. Okay. Anyway, so there's something I need to fix here. So in option in molecule A, this is not 12. This must be 6. Right, that's the total number of electrons it has. Okay, so 3 times 6 is 12. 12 plus 35 is 47. 47 plus 7 must be 54, not 78. This must be 54. Okay, let me make that correction. 54 electrons. Okay, so in this case, again, carbon has 6 electrons. Okay, so I need to write 6 here. Okay, so 3 times 6 is 18. 18 plus 8 is 26. 26 plus 8 is 34. We only have 34 electrons here. Then when it comes to option C, we have carbon, carbon, carbon. Common bonding pattern is fulfilled by carbon hydrogen bonds for carbon. We have this situation. We have C3, H, let's see, 1, 2, 3, 4, 5, 6 plus 6, 3 is 9, and then nitrogen. Okay, so this should be 3 times 6 plus 9 plus nitrogen has 7 valence electrons. Not 7 total electrons, 5 valence electrons. Therefore, if you add them up, you're going to have 18, 18 plus 9 plus 7, which is say 27, 27, 35, right? 18 plus 9 is 27. 27 plus 7 is Actually 34. Is it 34? Yeah, 34 electrons. Okay, 34 electrons. Okay, so here's the thing. So they both seem to have the same number of number of electrons, actually, both B and C. The only issue with B is, all right, so B has this part sticking out. Okay, in B we have this part sticking out that's going to act as a barrier for the molecules to come close to each other. It's a good thing for the intermolecular forces such as hydrogen bonding and the dipole-dipole forces, because it's more polar, and then hydrogen bonding interactions. When it comes to dispersion forces, that is going to be an umbrella. Okay, that's going to, or like a branching, kind of like a branch that's going to act as a barrier for the molecules to come close to each other. As a result of that, you're going to have the dispersion forces weakened in B compared to C. Okay, in C is a linear molecule, which does not have this branching. Therefore, you have a greater surface area of contact, which is going to strengthen the dispersion forces. Okay. Anyway, so A will have the strongest dispersion forces. Strongest. Okay. And then B will have the weakest. Okay, C should be in between. So B, C, and A. Let's say B, C, and A is option D. Okay, so you can see that that's the correct answer. All right, moving on. Let's do another one. I think question 2 here. Yeah, let's see. So we're talking about the boiling temperatures. Okay, so boiling temperatures. Let's take this picture. Okay, boiling temperature, increasing boiling temperature, which is going to be a function of IMF strength. Okay, so let's see. Now, if you consider these molecules, all of these are polar molecules. Okay, because you have a dipole moment going in this direction, and then something like that. It's going to be rotating, and then you have a dipole moment here as well. Okay, so all of these are polar molecules. Therefore, you're going to have dispersion and dipole-dipole. And none of them has hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Therefore, no hydrogen bonding. Okay. And now what we need to determine is which one is going to have the strongest interactions. Okay. So I really like B. The reason is it's going to, because of the ring structure, it's going to be a flat molecule, and also it has a lot of electrons with sulfur. Because of the presence of sulfur, and then the long carbon chain, and then five member ring over here. We have 1, 2, 3, 4, 5 carbon atoms, which is going to give us 5 times 6, 30 electrons. Okay, so therefore it's gonna have the strongest overall intermolecular forces. Okay, so we are between options B and D here. Okay. Now between A and B, okay, so we need A and C. We need to decide which one's going to have stronger intermolecular forces. Okay, so even though the dipole forces are going to be stronger here, okay, if we count the electrons, here we have carbon, carbon, carbon at the ends and bends. Okay, and the common bonding pattern is fulfilled by carbon hydrogen bonds. Okay, and then if you add up the if this is C3, H6, and oxygen. Okay, and then that is going to be 3 times 6, 18, plus 6 plus 8. So that is going to be 24, 32 electrons. 32 electrons. And on the other hand, in C, we have 1, 2, 3, 4, 5 carbons. Common bonding pattern, carbon hydrogen bonds. Okay, this should be fine. And this should have 3. 1 more, and this should have 2 more carbon hydrogen bonds. Okay, if we count them, we have carbons. We have 1, 2, 3, 4, 5 carbons. hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Okay, and then 1 sulfur. So from carbons, we have 6 times 5, 30 electrons. From hydrogens, we have 10 electrons, and from sulfur, we have 16 electrons. So altogether, we have 30, 40, 56 electrons. Okay, because you have a lot more electrons in C compared to A, the dispersion forces should be much stronger. It has dipole, plus it has stronger dispersion forces. Okay, and also compared to, I don't know, this is if you can remember, we talked about this fake 15 electron rule. Okay, so let's see that we have 24 more electrons than molecule A. Okay, therefore the dispersion forces must be strong enough to outweigh the little bit stronger dipole forces of A. Okay, therefore C should have strong in overall intermolecular forces than A. So that's going to be the consensus. Okay, so A should have the weakest, therefore the lowest boiling point, and then C, and then B should have the highest. Therefore our answer is going to be option B. Okay, so that is that. And moving on, seems to be fine, but let's check one question here. All right, it's loading. Here you go. Okay, a substance is generally insoluble in water, but the solubility values are shown in the table to the right, which peg diagram best represents how salicylic acid mixes with water. Okay, now generally insoluble, when you increase the temperature, you see that the solubility increases. Increasing temperature increases solubility. This tells us that the mixed state should have a higher potential energy than the unmixed state. Okay, it's increasing. You can see that high temperatures favor the state with high potential energy. It has to be the mixed state, because that's the only reason why the solubility increases with increasing temperature. Okay, so therefore we need to pick one of that. Okay, that is not this, because mixed state has a lower potential energy. That is not this, because solubility depends on the temperature. If we have a Pregg diagram like this, solubility does not depend on the temperature. And then it can be this. Okay, actually, you know what? It has to be this. Okay, because it's generally insoluble. And then in both these cases, we have the mixed state has a higher potential energy, but we are told that it is generally insoluble. Okay, meaning the mixed state has a lower number of configurations. Therefore, I would go with this option over here. Okay, usually if it is generally insoluble, then the number of configurations should be lower in the mixed state. Okay, that's why we went with that. So that's our option. Let's see. Yep, that's the correct answer. Okay, moving on to question 27, which is not great. Let's see. It is ranging from 9 to 100%, which is weird. Anyway, I have a feeling that these are different questions. Anyway, so let's think about question 7. Oh, this cannot be that hard. Okay, here's the thing. The question is, how many atoms can engage in hydrogen bonding interactions in this molecule? Okay, so we have this. Oh no, we can't. I took a picture, but I didn't use it. Let me see. All right, let's work on this. This atom. There are 2 hydrogen atoms here and 1 here. And this atom, and this atom can engage in hydrogen bonding interactions. So if we count them, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. It should be 9. Okay, that's why it is 9. All right. So here we have 2, because 2 hydrogens means we have 2 hydrogen atoms that can involve in hydrogen bonding interactions there. That's why the correct answer is that. Let's do another one of that. And question 9. Again, how many atoms can engage in hydrogen bonding interactions? The same question. Let's do this here again. So we have this atom 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 9. Okay, and then let's do another one. Question 8. How many atoms again? Okay, anyway, so if you take a picture one more time, let's count them again. 1, 2, 3, 4, 5, 6, 7, 8. Should be 8. All right, so I think you're getting the picture here. Okay. That's it. Yeah, by the way, I'm going to do one other thing here, so just to help students out here. Okay, so here, if you draw hydrogen bonding interactions with another molecule, let's say water, you can have like this. Okay, or water can have hydrogen bonding interactions with this hydrogen, like this, or like this, or like this, or like this, or like that. Okay, and those are the possible hydrogen bonding interactions. Okay, and then let's say that we have a molecule like this. Okay, even though this molecule cannot have hydrogen bonding by itself with another molecule of its of the same type, it can have hydrogen bonding interactions with this molecule over here, because this hydrogen can be sandwiched between this oxygen of the other molecule. Okay, so only requirement is for hydrogen bonding interaction, you need to have a hydrogen atom covalently bonded to nitrogen, oxygen, or fluorine in one atom, and then the other molecule. Oh, I'm sorry. Let me rephrase that. We need to have, the condition is we have a hydrogen atom covalently bonded to either nitrogen, oxygen, or fluorine in one molecule. In the other molecule, we need to have nitrogen, oxygen, or fluorine. That is it. Anyway, so moving on. That is an unfortunate statistics, actually. Okay, that's one of the easiest question to count the number of atoms that can engage in hydrogen bonding interaction. Just out of curiosity, I want to see question 4. What's going on there? Which is a little bit. It's a different question. Okay. So anyway, the peg diagram to the right indicates mixing behavior of A and B. Based on the peg diagram, which of the following interactions are the strongest? Okay. Now here's the thing. This should be one of the easiest. Okay. So we have this mixed state over here. That means had a higher potential energy. That means mixed state has weaker interactions. Okay. So in the mixed state, we have interactions between A and B. Okay, A and B. And in the unmixed state, we have stronger right now. Okay, what we have is AA interactions and BB interactions. So strong. Okay, so AB interactions are weaker. They're asking for where the interactions are strongest. Okay, so AA and AA and BB interactions are stronger. That should be 1 and 2. That is this. Okay, yeah, there you go. All right, moving on. Question 28 seems to be fine. 29 seems to be fine. And question 30 can be better. Let's pick one. Let's pick question 2. Random question 2. Okay, here we go. So let's see. Here's what we have. We have an IR spectrum, and then we have a visible or UV-based spectrum. Okay, how do you know that this is UV-based? Remember the colors of the rainbow? It goes from red to violet. Red is around 700 nanometers. Well, it is around 400 nanometers. Okay, you can see that we have 400 here, and then this should be the visible range, and then this should be the UV. This is UV-Vis. Okay, and that's how I know this is UV spectrum. Anyway, and then below red we have infrared, IR. Okay, that should have longer wavelength than 700 nanometers. So the wavelength here is greater than 700 nanometers. Okay, so the shortest wavelength, therefore the shortest wavelength here should be 3. Okay, because that's the only only peak in the in the UV visible range, and all the other two are in the IR range. Okay, so 3 should be the shortest, and what we see, 3 has the shortest wavelength in option B over here. And then between 1 and 2, what we have is the wave number here. Okay, so the wave number means 1 over lambda. Okay, so if you have a higher wave number and the wavelength are inversely related, that means higher the wave number, shorter the wavelength. So we have a higher wave number in 2, therefore this should be a shorter wavelength, shorter than this one, longer. Right, so because 2 has a higher wave number, higher the wave number, shorter the wavelength. Anyway, so 2 should be in the middle, in other words. Okay, so it should be, this is the only one we have 3 with the shortest wavelength. It has to be this. Here's 2 in the middle, and then the longest wavelength in 1. Therefore this should be your answer, option B. There you go. All right, moving on. Let's pick another question from here, question 31. Let's pick question 5. All right, question 5, you are given the mass spectrum, and then let's take a picture. Okay, here's the mass spectrum. Given the mass spectrum and molecular structure of propanoic acid, what is the most likely fragment for the peak at 29? At 29, okay, we're talking about this guy over here. Okay, so here what we need to do is we need to count, right? So let's start with the bottom one. This is easy to count. Carbon is 12. That's the relative atomic mass of carbon. And then the hydrogen is 1. We have 3 of them. This should be 15. This is not 29, so this is out. And CHO, carbon is 12 plus 1 for hydrogen, and 2 times oxygen should be, oxygen is 16. 16 times 2 is 32. So this is much greater than 29. So that is out because oxygen itself is 32 here. And then the next one, carbon is 12. 12 times 2 is 24, because we have 2 carbons here, plus 5 is 29. So this must be our answer. And then when it comes to the next option, okay, it's going to be much greater than 29, because carbon is 12. We have 3 of them, that is 36, plus 5 for hydrogen, and oxygen is 16 times 2 is 32. So this is not it. Okay, this is not 29, so it's out. So the correct answer is option B. Okay, so let's see. Yeah, that's the correct answer. Okay, so let's pick question 7 as well, just to see what's going on there. Given the mass spectrum and compound above, which of the below was likely lost? Now this is what is lost from the molecule to generate the peaks, or not peak labeled A above. All right, so the peak labeled A has a mass of this much. So let's determine the mass of that roughly, at least. Okay, so we have 80 and 120 here. Let's see, 120 and 160 is divided to 1, 2, 3, 4. Okay, so we have four difference between 120 and 160 is 40. 40 is divided into 4. That means each tick over here should be 10. Okay, now anyway, let's just determine that. Anyway, so this over here at A must be 90, between 90 and 100. So let's say it's around 95. Okay, and the molar mass of this compound is 160, 170, between 170 and 180. This is 170 and this is 180, so it should be around 175. 175. Okay, so what should be lost to get this? Okay, now let's see. If we just lose carbon, that is just minus 12. Okay, but we can see that, let's say this is 175, between 95 and 175 the gap is around 80. Okay, we need to lose 80. Okay, but if you lose just carbon, is minus 12. That's not going to work. Bromine is 79.9, so this is 80. Hydrogen is only 1. That's not going to work. Okay, and then CH2 is, carbon is 12, hydrogen is 2, should be minus 14. So that is out. So the correct answer must be option B. We need to use bromine to get from 180 or 175 to 95. Okay, so let's see. Yep, that's the correct answer. So I mean, how do I know the atomic or relative atomic mass of bromine? Okay, you just go to the periodic table and read the number under the atomic symbol of bromine. That happens to be 80. That's the relative atomic mass of bromine. And if you take the molar mass of that, if you take 1 mole of that, of bromine, it's going to have 80 grams, so 79.9 grams. Okay, and that's how I know that. Anyway, moving on. It's all in the periodic table. Let's go to question 4 in question 32 to shed some light here. If I can. There you go. All right. Now, some of the formulas below could be either empirical or molecular formulas. However, some of them can only be molecular formulas. Which of the below must be a molecular formula? Okay. Now, here's the thing. Okay. If it can be both empirical and molecular, okay, that means it should have the lowest whole number ratio. Okay, so lowest whole number ratio, empirical, okay, has the lowest whole number ratio. Okay, and then sometimes what happens is when it comes to molecular formula, you cannot divide this subscript by any other number anymore. Okay, that means if you have that situation, your molecular formula is also the empirical formula. Okay, let's consider what we mean. Let's consider C2H5. Okay, so this is the lowest whole number ratio between 2 and 5. You cannot make this more simpler. You cannot make this 2 and 5 any lower. It has to be 2 and 5. So this can be both molecular or empirical. C4H8. Okay, so C4H8 can be simplified further to, so because you can divide 4 and 8 by 4, right? So therefore you can write the empirical formula of this as C1 and H2. So this is going to be the empirical formula for C4H8. So this must be a molecular formula. Okay, because this cannot be, this must be molecular only. Okay, because we know that this cannot be an empirical formula because 4 and 8 are not the lowest whole number ratio. We can further simplify it. Because we can further simplify it, okay, this can only be a molecular formula. Anyway, let's move on to the next one, C6H14 and O. Okay, so ratio between here is 6, 14, and 1. Okay, if you this cannot be further simplified, so therefore this must be an empirical formula. This is an empirical formula. Okay, and the same thing here, 2, 14 and 7. Okay, you cannot further simplify it. This is the lowest whole number ratio, therefore this should be an empirical formula, which can also be a molecular formula. Okay, so this is an empirical formula for sure. Okay, and then this can be a molecular formula. Okay, but this guy over here cannot be an empirical formula. This has to be a molecular formula. Anyway, making that distinction here. Right, moving on. Question 33. Let's do this quickly. Let's see. All right, so here you go. Elemental analysis of an unknown molecule gives an empirical formula of C2H6O. Given the data above, what is the most likely structure for this unknown molecule? Okay, let's see. Now this unknown molecule should have CH bonds, CC bonds, and CO bond. Okay, if you look at option A cannot be your answer because you do not have CC bond. Okay, and then option B cannot be your answer. Okay, because you have this OH, right? We don't have OH in IR, no OH bonds in the IR spectrum, so that is out. And then option C cannot be because you don't have C double bond O bonds or OH bonds in the IR spectrum, so that is out. Okay, and then give me a second. This given the what is the most likely structure? Okay, so we're gonna have a problem here. You don't have OH or C double bond O, and then here we have OH, which you don't have OH in the IR spectrum, so that cannot be. Here the data about what is the most likely structure for this unknown molecule. None of these molecules match with the IR spectrum. Okay, because we don't have OH in the IR spectrum. If we had OH, okay, I think that was the idea, maybe. Okay, let's think about this for a second. Okay, if we had OH, okay, it could be either this or this. Okay, let's say that we don't have C double bond, no, therefore this is out. And then what we need to do is we need to determine we have the empirical formula, okay, which is C2H6O, and also based on the mass spectrum, we have 1, 2, 3, 4, 5, 6. I'm going to say this is smaller mass 46. Okay, so then we need to use that information. So if you consider this molecule over here, this is C2H6O, that is 2 times 12, 24, plus 6 plus 16. Okay, that's going to be 30, 46. And this molecule over here has the molar mass of, let's say, C2H1, 2, 3, 4, 5, 6 plus O2. This is definitely greater than 46. Okay, 2 times 12 is 24 plus 6 plus 2 times 16 is 32. So if you add them up, 24, 30, 62. Okay, so this is out if that is the case. I think the idea is there's an error in this problem. Okay, there should be an OH bond in the IR spectrum. Otherwise, it's not going to work. And then based on that, this should be your answer. Okay, now that's an error here. Okay, let's see. Yeah, no, the option here cannot be correct because you don't have carbon-carbon bonds in this molecule. Okay, so that is incorrect. So I need to fix that. Anyway, that is an incorrect option. Okay, so okay. Anyway, moving on, let's do 35 really quickly. I think, given the data, which of the following best describes HBr bond versus BR-BR bond? Okay, so let's go here. Now, here's the BR-BR bond. Here's the HBr bond. HBr bond is stronger. Okay, reason it has a lower potential energy or internal energy. Okay, meaning stronger. Lower energy meaning stronger. Okay, also it is shorter. Why? You can see that the bond distance is given by the distance reading at the minimum. So here's the bond length for HBr, and for BR-BR it's going to be much longer. Okay, so HBr is stronger plus shorter than BR-BR. Anyway, that's it. That's the first one. Shorter and stronger. That's the correct answer. Not the same length. That is incorrect. HBr is shorter. Yes, and weaker. No, it is stronger because you have a lower depth. HBr is longer. No, HBr is shorter. So correct answer is option A. Okay, so that is that. And then maybe, I think, almost there now. Let's do question 38 really quickly. What are the molecular geometries for each of the atoms indicated in the molecule above? Okay, so here we have a carbon. Let me actually do this. Okay, now here we have a carbon, hydrogen. Okay, so, and here we have a carbon, 2 carbon hydrogen bonds, and then we have this lone pair here. So you need to do that because we need to have a lone pair here because we have 3 bonds around this nitrogen. That means 6 electrons. And the idea is in the Lewis structure, we need 8 electrons around it. We need 1 lone pair to make it have 8 electrons around nitrogen. That's how we know that. Okay. Anyway, so based on that, now around the third one, we have, let me use a different color actually right now. So we have 1, 2, 3 electron domains. Okay, 3 electron domains. Okay, now the electron domain geometry is trigonal planar, and all of these electron domains are bonding as well. They are for trigonal molecular. Give me a second. I need to organize this in different better way. So let's say 3 electron domains, 3 bonding pairs, 3. So molecular geometry must be trigonal planar. Okay, and then when it comes to 2, we have 4 electron domains, 1, 2, 3, 4. Okay, and all of them are bonding electron domains. If you have 4 electron domains, they're going to arrange in tetrahedral geometry in the space to minimize the repulsions between them, because all of them are bonding electron domains. The molecular geometry is also tetrahedral. Okay, and 1. Okay, you have, let me actually erase these guys first. Okay, in 1, what we have is we have actually, I'm going to redraw it. Okay, here's what we have in 1: hydrogen, lone pair, hydrogen, and hydrogen. Okay, so we have 1, 2, 3, 4 electron domains. Okay, and then so 4 electron domains. Therefore, electron domain geometry is tetrahedral. Okay, and then only 3 of them are bonding electron domains. If we have this situation, you're going to have molecular geometry of trigonal pyramidal. Okay, because if you just look at the bonding side, it's going to be like a pyramid, trigonal pyramid. So it's going to be trigonal pyramidal. All right, so those are the answers. Let's see if we can have this. One is, you're talking about the molecular geometries. One is trigonal pyramid. Okay, this is out. And 2 is tetrahedral. So 2 is tetrahedral. So these 2 are out. And then 3 is trigonal plane, and that is correct. So option B is correct. Okay, option B. All right, moving on. Yeah, last question. All right, let's see. Let's pick random question 2. Which of the statements describes a covalent bond? Bond formation is favored by decreased electron density between atoms and electron localization. No. So no. Okay, covalent bond formation delocalize electrons between 2 atoms. Okay, between atoms, you're gonna have a high electron density now. Okay, so this is absolutely wrong. It's not localized. It's gonna be delocalized. Delocalized between 2 atoms. So that is incorrect. And then option B is incorrect because we know the first one is incorrect. The bond length and strength are determined by the minimum in internal energy. Yeah, that is true. So here's what we have. Okay, here's the distance. And then what we had is this situation. Okay, so the bond strength is related to the minimum. Lower the energy, lower the internal energy, or lower potential range of internal energy. Stronger the bond energy, or bond strength. Let's call it bond strength actually. So that's going to be even better. All right, bond strength, and then the bond length is determined by the distance over here. That is the distance between the atoms at the minimum is going to give the bond length. This is the bond length. Okay, so that is correct. And then the last option, let's check anyway. Okay, the atom in a bond vibrate around a distance where the internal energy is the highest. No, internal energy is the lowest. Okay, so the bond is the optimum distance between the atoms is over here. This is the optimum distance. Okay, it's going to vibrate around here, so it's going to be a little bit higher, a little bit lower, but it's going to be on average around this value. So that is incorrect. So option C is correct there. Okay. Let's pick another one here. See question 9. Ask question. Okay. Given the incorrect Lewis structure above, which of the options above indicate the errors? Okay, you can see that incorrect number of valence electrons. If we count the electrons, okay. No, I can't draw here. Let me see. Picture. Okay, so we have nitrogen, which has 5 valence electrons, and then we have oxygen, which has 6 valence electrons, and then we have chlorine, which has 7 valence electrons. If we count them, we're going to have 12, 18 valence electrons, or 9 electron pairs. Okay, let's count the electron pairs now. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, we have the correct valence electron count. So this is not the case. Okay, and then let's get rid of that. Okay, and then let's look at the central atom. Central atom is usually the atom with the highest bonding capacity. Nitrogen has a bonding capacity of 3. Let me see. Nitrogen has a bonding capacity of 3. Let's say bonding capacity. Okay, this is 3, this is 2, this is 1. Because nitrogen is in the center, the bonding capacity wise it is totally fine. The higher bonding capacity atom is in the center, so that is not it. Okay, last let's look at the octet rule. Not satisfied. So the idea is every atom should have an octet around it. If you think about oxygen, we have 1, 2, 3 pairs of electrons. That means only 6 electrons. There's no octet. That is absolutely correct. And then nitrogen is fine. We have 1, 2, 3, 4. That is 8. And fluorine is fine. We have 1. No, fluorine is incorrect as well because we have 1, 2, 3, 4, 5, 10 electrons around fluorine, which is not possible. Okay, so this is violated. The correct answer is 3 only. All right, so I think that's it. So that covers most missed questions in this quiz. I hope this helps. Have fun in the final exam, and what are the exams you have to take? Bye, everybody.